Hello, Math 150. Tonight we're going to look at graphing logarithmic functions. I want to review a problem with you guys, which I think is really important to understand when we're graphing logarithmic functions. So I want to go back to the problem 2, the x equals 0. Now, by now, with the number of times you've seen this pop up, you should know that there's no way you can take 2, raise it to a power, and get 0. But the idea is how close can we get to 0? So remember that 2 to the 0 is actually going to be equal to 1, the way it's defined. And then as we drop this exponent, we're going to keep dividing our answer by 2. So 2 to the negative 1 is 1 half. 2 to the negative 2 would be 1 over 2 squared, which is the same as 1 fourth. 2 to the negative 3 is going to give us 1 over 2 to the third, and that's 1/8. So as we continue in this pattern, we're getting closer and closer to 0, but we're always going to have just a little bit. We're always going to have just this fraction. As we keep going down, we're going to keep cutting this fraction in half. We're going to go 1/16 to 1/32nd, 1/32nd to 1/64th. That 1/64th will then drop to 1 over 128, and that will drop to 1 over 256, and so on and so on. But what's happening is, as the exponent goes further and further down, our value is getting closer and closer to 0. So the question is, what's the closest we can get to 0? And that's with the largest negative exponent possible. So this is not the best mathematical notation, but it's going to illustrate my point. What I want to do is I want to raise 2 to the negative infinity, and then that would get me 0. Now, again, we're not really allowed to do this because we can't input infinity as a real number, but this is the concept I want you to understand. Now, thinking about this in the logarithmic sense, this would say that log base 2 of 0 would equal negative infinity. This is going to be important when we go to graph logarithms, because what this is telling us is that whenever the inside of a logarithm equals 0, that means we have a vertical asymptote, because that is the only way we can show that our graph or our values are approaching 0. So again, this is kind of the most important thing to remember as we look at graphing logs today. When the inside of the log equals 0, at that x value, we're going to have a vertical asymptote. Let's take a look, see if we can put this into practice. So on this first one, we're asking to do log base 2 of x. And again, you may want to remind yourself that log base 2 of x, again, the way that works is we're saying 2 raised to this answer, to this output, is going to give us the x value. So keep that in the back of your mind. But for right now, we're going to ask, where is the stuff inside the logarithm equal to 0? Well, in this problem, the only thing we have inside the logarithm is x. So x equals 0 when x is 0. That's pretty straightforward. What that means for us is that we're going to have a vertical asymptote at x equals 0. So I'm just going to draw that right now. That's going to be at the y-axis. So x equals 0 is the y-axis. We're going to have a vertical asymptote right here along the y-axis. So now the next thing that we're going to want to do is we're going to want to find out where is the x-intercept for this. Now remember, x-intercept, say, take our function and set it equal to 0 and solve this equation. Now, the way we get rid of a log base 2 is we do exponential base 2 to both sides. You may remember that from our session on solving equations. So when we plug in log base 2 of x on this side, we plug in 0, exponential base 2 and log base 2 cancel. We are going to be left with x equals 2 to the 0, which is 1. So we know we're going to have an intercept at 1. I'm going to label this as 1 just so we have a little more space here so you can see it. So we know we're going to go through that point right there. Well, once you know this, the general graph of the logarithm is always going to be the same, okay? Let's just look at 2 more values to give you an idea of what's going on. If we asked about end behavior on this, if we asked about what's happening to log base 2 of x as x goes to infinity, where's log base 2 of x going? Well, as we plug in larger and larger values for our x, okay, we're saying 2 raised to what value is giving us large values? 2 raised to what value is giving us this infinite value? Well, the only way we're going to get that is if we are going to have an infinite result. So that means as we go all the way to the right, our graph is going all the way up. We're headed off in this direction. All right. That's going to be enough to put this graph together. We're now going to say it's going to use this vertical asymptote coming from the bottom. It's going to go through our x-intercept there, and it's going to curve like this. This general shape is the shape that all logarithmic functions are going to have. So this is what we're going to have for the graph of log base 2 of x. This is how it's going to look. The idea in all these problems is to find the vertical asymptote first, then find the x-intercept, and then find the end behavior. And end behavior means x going to infinity, okay? So that's the idea. If we can find those three things, we can put them together. They're always going to have this sort of same shape right here that we're seeing in this graph, and we're going to be able to do these problems. So let's look at 2 or 3 more today and make sure you guys are comfortable with graphing these functions. So in the next one, we've got the log of x minus 6. Remember, there's no base written here. If there's no base written there, it's assumed to be base 10. We don't have to write it when it's base 10. That's the common logarithm. So first step, find out where the vertical asymptote is. That vertical asymptote will be when the inside of the logarithm is equal to 0. So that's going to get us x equals 6. So we know we have a vertical asymptote at x equals 6. I'll go and I'll draw that in here. I am going to label this value right here as 6 for our purposes. And we're going to draw a vertical asymptote at that value. Now, with the logarithm, remember, it's not going to approach the top and the bottom. It's going to be one or the other. We're going to need to figure that out. The next step, and again, that's finding the vertical asymptote. The next step is to find the x-intercept. So to find the x-intercept, we're going to take this function and we're going to set it equal to 0. So this is log base 10 of x minus 6. We're going to set this equal to 0. The way you get rid of log base 10 is you do exponential base 10. I need to do it to both sides. So putting log base 10 in here of x minus 6 and then putting 0 in here. 10 and log base 10 cancel. We get x minus 6 equals 10 to the 0. 10 to the 0 gives us that value of 1. And when we add 6 to both sides, we're going to get that x is equal to 7. So I'm just going to go and I'm going to label 7 right here. And I know this is an x-intercept. So from here, we're going to ask what happens to log base 10 of x minus 6 as x goes to infinity. Okay, what's going to happen? Well, again, basically what we're saying is 10 raised to this answer is going to give us infinity because as x goes to infinity, x minus 6 is going to infinity. So 10 raised to what power is going to be infinite? Well, again, that's going to be infinity. So we know that the inputs are going to infinity and the outputs are going to infinity. So what that tells us is we're going to end up in that region again up here. So we know we've got to use this asymptote. We know we've got to go through that x-intercept. And we know we've got to go in that direction. So we see the same logarithmic graph, the same shape every single time, okay? Let's take a look at this next one. In this next one, we've got the natural log of 4 minus x. Now remember, natural log is log base e. So again, I'm looking for the vertical asymptote first, and that's going to be where the inside stuff equals 0. Add x to both sides, and we're going to get x equals 4. So we know that we've got a vertical asymptote at x equals 4. So let me go and let me put that in. Now on this one, I want to find the x-intercept. I'm going to take that function, I'm going to set it equal to 0. I'm going to do the natural log of 4 minus x equals 0. And this is going to help me find the x-intercept. This time I've got log base e. Remember, natural log of x is the same as log base e of x. So the inverse of natural log is exponential base e. So I'm going to do e to the both sides. So I'm going to get e to the something equals e to the something. The ln of 4 minus x gets put in here. The 0 gets put in here. E and ln are inverses acting directly on each other. We're going to be left with 4 minus x. And e to the 0 is going to equal 1. So we're going to end up here. If I add x to both sides, and I subtract 1 at the same time, what we're going to find out is we're going to get that 3 equals x. So we now know that the x-intercept is at 3. Okay, so there's 3. So on this one, it's kind of interesting because in the last two, we were going to the right. If I try to find the end behavior on this one by letting x go to infinity, we're going to get into a little bit of trouble because now we're going to end up doing 4 minus large values, and that's going to be a negative. Natural logs cannot have a negative in the inside. So that's not going to be in the domain. The domain of this is going to be when we're less than 4. So this is going to be undefined. There's going to be no graph on the right side of the asymptote. The graph is going to happen on the left side instead because that's where the domain of this is. So the end behavior we're curious about is not as x goes to infinity. It's the other side. It says x goes to negative infinity. So now again, we're saying, and remember, this is a base E problem. So if I rewrite this as log base E as x goes to infinity, what we're really saying is E raised to what power gives me this 4 minus, and I need to be clearer on this. I left out my negative. 4 minus, and it's going to be a negative infinity. That's going to make it up. It's going to be 4 plus infinity. It's going to be 4 plus a large number. So E raised to what power is going to give me something that's going to infinity? Well, this is going to have to be infinity. So in this case, we're being told that X is going to negative infinity. That means it's going all the way to the left, but the output is going all the way up. That means our graph is actually headed in this direction right here. So when I go to graph this particular function, I'm going to use the asymptote, go through 3, and then continue up in this direction. Now, this guy has a y-intercept. The rest of our problems that we saw did not have a y-intercept. You could go and you could find that y-intercept in this one. When you go to find the y-intercept, that just means plugging in 0 for x. That would be the natural log of 4 minus 0, and that's what the output would be. When we simplify that, we just get the ln of 4, okay? So we would label this as the natural log of 4. And a way to think about that is what we're saying is we're talking about log base E of 4, okay? So remember, E is roughly 2.7. So we're saying this value, like 2.7 raised to what, is going to equal 4. So it's going to be between 1 and 2. So this value is actually going to be somewhere between 1 and 2. So I don't have the best labeled graph here. I put a 1 up there. I can put a 2 up there. It's going to fall somewhere in between. And that's the graph of ln of 4 minus x. Notice this one is on the left side of the graph. All the other ones we did ended up being on the right side of the graph. And again, that's because the domain says that we have to keep this positive. So we stayed on the positive side. That was the first example. In the next example, we have to keep this positive. That means we're using values greater than 6. So we stayed on this side. In this one, we have to keep this inside positive. Well, that says x is going to be less than or equal to 4. And that's why we stayed on this side. Let's take a look at one more example. Okay, so on this one, we've got 2 minus the natural log of x plus 8. Here's my suggestion to you guys, at least at first, until you get more used to it, okay? My suggestion is to start the same way and find out what makes that inside 0. Find that vertical asymptote. To me, that's the key to graphing these logarithms. So we're going to do x plus 8 equals 0. That's going to get us x equals negative 8. And that is where the asymptote is going to lie. So I'm going to go ahead and I'm going to put negative 8 right here. And I'm going to make that an asymptote. Okay, so now what I'm going to do is I'm actually going to focus on graphing just this part, just the y equals negative ln, not even the negative. I'm just going to do the ln of x plus 8. Okay, so what we're going to see now is we want to find that x-intercept. When I find the x-intercept, I'm going to do ln of x plus 8 is equal to 0. Remember, this is e. That's going to get rid of the ln, so I'm going to do e of the both sides. The ln of x plus 8 goes in here, 0 in there. E and ln are going to cancel. We're going to be left with x plus 8 equals 1. Subtract 8 from both sides, and we're going to x equals negative 7. So we know there's negative 7. That's where that graph is going to go. If we now do the end behavior for this, the ln of x plus 8 as x goes to infinity, well, again, e raised to what power is going to give us something that's going to be infinite? That's going to be infinity. So we know we're going to end up in this direction. So this is not the final answer. This is just the ln of x plus 8, and it looks like this. Okay, so that's y equals ln of x plus 8. Well, what's going to happen if we multiply that by a negative 1? Because that's what we're being asked to do here. We're being asked to multiply that by a negative 1. Well, all that does to your graph is it just flips it over the x-axis. Sorry about that. Okay. This value right here is going to stay exactly the same, but now instead of going below the axis, it's going to go above the axis like this. This value right here is going to get flipped over. So we're going to see this graph just flip over the axis and be a mirror image. And that's going to be y equals negative ln of x plus 8. Okay. We're still not done though, because our graph asks us to take that purple graph and add 2 to it. We got to go up 2 higher. So now the idea is to take this graph and go up 2 higher. So what that would mean is everything in our graph now has to move up 2 units. So this point is going to move up 2 units. It's going to end up here. This point is going to move up 2 units. It's going to end up here. This point is going to move up 2 units. It's going to end here. This point is going to move up 2 units. It's going to end here. So as we go to graph that, everything will just be moved up 2 units. It's going to keep the exact same shape, but it's just going to move up 2 units. The final graph is this green one. It's 2 minus the ln of x plus 8. So by using kind of the idea of transformations, we can get this to work. So that's one way you could approach this graph. You could just focus on the ln of x plus 8 first, and you could do it that way. So that's one way to think about handling this. Now, another way you could try to graph this without using transformations is you could try to do it directly. Now, doing it directly, nothing's going to change when you find that asymptote. You're still looking for where x plus 8 is equal to 0. That's still going to give you this asymptote of negative 8, so that's not going to change. But what is going to be a little different is when you find the x-intercept. So now when I find the x-intercept, I've got 2 minus the natural log of x plus 8. I want to make that equal to 0. That's going to say that 2 is equal to the natural log of x plus 8 when I add ln of x plus 8 to both sides. So that's going to put me there. Now I'm going to do e to both sides to use the inverse of ln. Putting 2 in here and ln of x plus 8 in here. I am now going to get e squared equals x plus 8. And now I'm going to subtract 8 from both sides. So I'm going to get e squared minus 8 equals x. Now another way to think about that is negative 8 plus e squared. And remember, e squared is a little bit less than 3. It's at 2.7. So when I add that 2.7 squared to 8, it's not going to be enough to make it positive. It's going to keep it over here. So that's where I'd end up. Okay, and now the benefit is we can actually label this point as negative 8 plus e squared. So now I've got my x-intercept, I've got my asymptote, I can go after my end behavior. Now, it's clear from the graph, since the x-intercept lies on the right side, the end behavior is going to be when x goes to infinity, because it's only going to show up on one side or the other. And we know we've got the x-intercept to the right, so we're going to do the end behavior as we go to x goes to infinity. Setting this up, we're going to say, let's see what happens when x goes to infinity. Now, what's nice about this is the 2 doesn't get affected. 2 is just going to stay on the outside. The negative is going to stay on the outside. And now we're going to ask, what about ln of x plus 8 when x goes to infinity? And whatever we get for this answer is going to go up here. So we're saying, again, this is base e. So e raised to what power is going to give us something that's going infinite? Well, that's going to be infinity. So basically the idea is that in this function, this is going to end up being 2 minus an infinite result. Well, 2 minus an infinite result, what that's going to do is that's going to make us go to negative infinity. Okay, because it's going to be 2 minus this really large number. So it's going to go to negative infinity. So that says as we go all the way to the right, we're going all the way down. So that's going to take us down in this direction down here. So now, when we go to graph this function, it's going to go from the top of the asymptote, it's going to hit our x-intercept, and it's going to go down in this direction. Okay, you could still find the y-intercept for this guy. Finding the y-intercept just says, hey, let's plug in 0 for x. If we find the y-intercept, what we're going to end up with is 2 minus the natural log of 0 plus 8. That's going to be 2 minus the natural log of 8. That can be labeled right there, 2 minus the ln of 8. So you could attempt to do this directly, or you could go and do it this way, where we said, let's go and do it through transformations. Both ways are perfectly acceptable. This green graph on this one and this green graph here are going to be the exact same graph. So totally up to you. If you want to take it directly, feel free. If not, you can do it using transformations. That wraps up our lesson this evening on finding the graphs of logarithmic functions. If you guys have any questions at all, please let me know. We're going to spend 2 days on the next section, okay, in this unit. So that homework's going to be spread out a little bit over the next 2 days. As always, any questions at all, please reach out to me. I'm more than happy to answer any questions you have. Have a great day, everybody.